Hello, and welcome to our virtual Black Hat presentation entitled Repurposing Neural Networks to Generate Synthetic Media for Information Operations. My name is Phil Tully, and I'll be joined later in this slide deck by my colleague Lee Foster. We work together at FireEye, where I'm a staff data scientist on FireEye's data science team, and Lee is the senior manager of information operations in FireEye's threat intelligence group. For a bit of background about myself, I've been at FireEye for 2 years, and I've been working at the intersection of cybersecurity and machine learning for over 5 years. In a previous academic life, I earned my doctorate in computational neuroscience, and nowadays I perform research and development on FireEye's malware and Intel product offerings. Lee and his team of Intel analysts specialize in identifying cyber-driven nation-state influence campaigns online. He holds a master's degree in political science, a second in intelligence and international security, and is currently pursuing a third master's in analytics. So some quick bookkeeping to start out at first. In this presentation, we're going to try to convince you that open source, pre-trained machine learning models can be leveraged to generate custom synthetic media for malicious purposes. After introducing some core background material, I'll dive into 3 successive proof of concepts for how this can be accomplished today in the text, image, and audio domains. I'm going to channel the 3 wise monkeys and organize these experiments into 3 sections: see no evil, hear no evil, and speak no evil. I'll demonstrate how to fine-tune pre-trained natural language processing, computer vision, and text-to-speech neural networks in order to generate customizable synthetic media. Lee will then wargame out these capabilities in the context of social media-driven information operations, or I/O, and assess the challenges underlying detection, attribution, and response in scenarios where actors can anonymously generate and distribute credible fake content. We'll start off with some background initial material, and for starters, it's worth pointing out that synthetic media is by no means a new development. Methods for manipulating media for specific agendas are as old as the media themselves. You'll see some of the more famous examples illustrated here, including when the chief of the Soviet secret police was photographed walking alongside Joseph Stalin before being retouched out of an official press photo after he himself was arrested and executed during the Great Purge. An image of the pyramids was altered to fit the cover of National Geographic magazine, shifting 2 of them closer together to emphasize their size. Digital graphic After Effects like this became prominent with the advent of Photoshop. Now, fast forward to 2016, where carefully crafted social media messages were being posted across several platforms in order to disrupt public discourse and influence online opinion leading up to the US presidential election. Then later in the 2010s, the term deepfake was coined. There were several viral deepfakes, including one targeting Mark Zuckerberg, screenshotted here, that was designed to be a warning about the future of digital manipulation. While deepfake videos, including techniques like face swapping and lip syncing, are concerning in the long term, our talk will focus on more basic and arguably more believable synthetic media generation advancements, including in the text, image, and audio domains. We'll provide evidence later in the talk how some of these are already being leveraged as part of I/O campaigns today. Social media has greased the wheels for this type of activity by providing anonymity, immediate global reach, and the ability to go viral, rife data disclosure, and most importantly, a seamless way to share content publicly. The low-hanging fruit nature of this threat environment was illustrated by previous work I was part of, led by John Seymour. 4 years ago at Black Hat, we demonstrated how to generate credible, synthetic text to manipulate social media users for the purpose of simulated phishing attacks. The Snapper bot was shown to combine the best of both worlds. The shotgun approach of phishing, think Nigerian print scams that take little effort and have relatively low success rates, and the more targeted approach of spear phishing that takes additional upfront research effort but typically pays off in terms of higher success rates. By seeding a machine learning model with content read off the target's Twitter timeline and generating text pertaining to their recent tweet history, then simulating this at scale, we could get click-throughs more often and with less effort compared with humans, all due to machine learning. Such generative machine learning models can also be used for good, too. A few examples covered by the popular press are shown here on the left. They can be trained to mimic the voices of those with degenerative speech or language disorders, allowing people to synthesize words in their own voice well after it's been lost. Museums have brought dead artists back to life using machine learning models to interact with visitors in compelling, educational new ways. And activists can narrate their own stories more safely by superimposing fabricated faces over videos of themselves, allowing viewers to more easily empathize without exposing anyone's identities. But as these capabilities proliferate, there are just as many, if not more, misuse cases that have arisen in the real world. A few of those are called out here on the left, including one case in which a scammer used an artificially generated voice of an executive's boss to fool the executive into handing over $240,000. Another in which deepfakers created disturbingly realistic porno videos of women using photos of them involuntarily scraped from the internet. And a last one where a computer vision model was used to generate fake profile pictures for a LinkedIn persona that socially engineered senior government officials. So there's existing evidence showing that machine learning can be used to generate synthetic media for evil purposes. And in this talk, we want to focus on one specific technical methodology that's drastically reduced the amount of time and effort involved in making this happen. Transfer learning is a paradigm for machine learning, in which we start from a large generic model that's been pre-trained for an initial task where copious data is available. We then leverage the model's acquired knowledge to train it further on a different, smaller data set so that it excels at a subsequent related task. This process of training the model further is referred to as fine-tuning, which typically requires less resources compared to training it from scratch. This is illustrated in the diagram on the left. Normally, when there are two separate tasks that need to be solved, a data scientist has to wrangle two separate data sets and train two separate models. In this example, a classifier on the left and a regressor on the right, independently, in order to ship them both to production. And transfer learning shortcuts this process. If task 1 is related to task 2 in a way that task 2 can benefit from the learned representations of task 1, then we can actually use the neural network trained to perform task 1 as a starting point for task 2, all while requiring significantly less initial data for task 2. You can think of this in more relatable terms. If I'm a professional tennis player, I don't need to completely relearn how to swing a racket in order to excel at badminton. In a technical sense, this fine-tuning can be accomplished in several ways. By lowering or freezing learning rates, by making architectural modifications to the network, or by only allowing updates in specific weights or layers. Transfer learning works because early layers produce features that capture general attributes of the training dataset, whereas later layers capture properties of the task it's being trained on. As such, a common fine-tuning approach simply involves freezing the early layers from the pre-trained model and retraining just the last layer using a small dataset for a new task. This is computationally much easier than training a new model from scratch, since most of the learned parameters are taken directly from the pre-trained model. A much smaller number of parameters needs to be learned during fine-tuning. So transfer learning allows certain tasks to be tackled and take less time, with less effort, and at a lower cost. In practice, though, this only works well when people share their pre-trained models. Lucky for us, the culture of machine learning research nowadays has given research to a rich open source model ecosystem. It's become commonplace for well-resourced industry and academic researchers to release their model checkpoints when their state-of-the-art or SOTA work gets accepted into a top-tier conference. Typically, this code is released in the form of GitHub repositories with extensive how-to guides, well-documented READMEs, and from my experience, they're generally very well maintained with lots of attention being paid to open issues and bug reports. Oftentimes, this allows other researchers and grad students to easily reproduce figures from the initial papers and potentially use these models in source code as a starting point for their own research projects. This process plays out on a loop, ensuring a healthy, self-reinforcing model supply chain and ultimately a quicker pace of scientific innovation. However, while this emergent model sharing ecosystem beneficially lowers the barrier to entry for non-experts, it also gives a leg up to those seeking to leverage open source models for malicious purposes. But just how much has this barrier to entry been lowered, though? As a starting point, and hopefully this statement shouldn't be too controversial, in security and especially the malware space, we know that adversaries use open source tools like Cobalt Strike, Empire PowerShell, and Mimikatz. And the same concept holds for synthetic media generation. If there are tools out there that make this easier to do, it's safe to assume that those tools will be used. To put this into perspective, we experimented with a pre-trained natural language processing neural net called Generative Pre-trained Transformer, or GPT-2, a pre-trained computer vision neural net called StyleGAN2, and a pre-trained text-to-speech neural net called Speaker Verification to Text-to-Speech Synthesizer, or SV2TTS. On the right-hand side, you'll see a chart showing these three networks that we'll dive deeper into on upcoming slides, followed by the self-reported resources that the authors used in order to develop their respective models. So what's striking about these figures, if and when they were available, is that The thousands of dollars, weeks or months of time, sheer training dataset sizes, and large GPU clusters puts pre-training well out of the reach of script kiddies and other low-resourced adversaries. StyleGAN 2's authors went above and beyond by more realistically quantifying resource usage from the idea inception all the way to the open source release, figures that might give even well-resourced adversaries some pause. In comparison, the fine-tuning experiments, which I'll go into next, can be each done in a fraction of the time, cost, data size, compute, and flops compared to these pre-training numbers. Whether it's a cloud-hosted notebook with GPU access like Google Colab Pro, or an AWS P3 instance reservation for just a single day, we're talking on the order of just tens of dollars to fine-tune one of these models. Skill-wise, fine-tuning is not necessarily trivial, but it's also not brain surgery. Authors or other open source contributors often release additional code and tutorials for how to fine-tune, so that all you really need to have is some working knowledge of Python to do this. Furthermore, it's important to point out that each of these models were released just within the last year, so our demonstration should be seen through the lens of the present. However, open source trends we point out here are accelerating, and the bar for generating credible content will likely lower even further in the years to come. So our first proof of concept will be in the image domain, where we'll demonstrate how to fine-tune StyleGAN 2 in order to generate custom portraits to impersonate a targeted individual. We'll start with a brief overview of StyleGAN 2, which, like its predecessor StyleGAN, is architected as a generative adversarial neural network, or GAN. GANs consist of two underlying networks that are pit against each other, hence adversarial. A generator, which generates new instances of data, and a discriminator, which evaluates these instances for authenticity by deciding whether each one belongs to the actual training dataset or not. In this way, the GAN can synthesize indistinguishably fake images based on a training dataset, which for the open source version of StyleGAN 2 used here was Flickr Faces High Quality, or FFHQ. A set of 70,000 human faces that are diverse in terms of age, ethnicity, and image background, but also in terms of the presence of accessories like glasses, earrings, and hats. So if you generate images from this off-the-shelf pre-trained model, you get results that look like this. Alternatively, you can visit this now infamous website that will generate a new sample from the pre-trained model every time you refresh the page. In either case, these images are not present in StyleGAN 2's original training set, but are completely fabricated from the generative model. These people, in fact, do not, nor never have, existed. Pre-trained StyleGAN 2 outputs random, high-quality, and highly diverse images that appear in a similar orientation as the images that it was pre-trained on. But it can also be fine-tuned on private datasets to generate outputs for a custom task that I, as a consumer of their open-source model, am in control of. In this example, we've downloaded a few hundred images of Tom Hanks from an online image search engine, run them through an automated cropping tool called AutoCrop, so that each of them are face-centered and 512 by 512 pixels as required by the pre-trained model, and simply continue training StyleGAN 2 by pointing it at this new smaller dataset using a slightly smaller learning rate. After less than a day of training on a single GPU, we then generated outputs from the fine-tuned model using a ready-to-use script available from the original repo. The three images you're seeing of Mr. Hanks on the right are fake. They're generated from our fine-tuned model. You could see that they exhibit a high level of resemblance to Mr. Hanks, and in theory, we could collect cropped images from any target of our choosing and perform the same exercise to generate arbitrarily many fake images of them. In summary, we can cheaply generate fake portraits belonging to a target of our choice, at scale, from freely available images of them on the internet. Our second proof of concept will be in the audio domain, where we'll demonstrate how to fine-tune SV2 TTS in order to generate custom voices from arbitrary text to impersonate a targeted individual. SV2 TTS is a complex, three-stage model that's capable of performing voice cloning, or text-to-speech from arbitrary text inputs to captured reference speech in real time. So how does this system work? It's comprised of three underlying networks. First, the speaker encoder is trained on thousands of speakers in order to learn an abstract representation of human speech and squeeze it into a compressed embedding of floating point values. Then, the synthesizer, which is based on Google's Tacotron 2, takes text as input and returns a mouse spectrogram, which is a numerical representation of an individual's voice. Lastly, the vocoder, which is based on Google's WaveNet, takes the mouse spectrogram and converts it into an output waveform that we can actually listen to. To emphasize how much data it took for this model to learn useful representations, the tool's authors state that it was pre-trained in over 2,500 hours of audio from over 8,500 individual speakers, which is just a Herculean task for the people involved in that dataset collection. So to demonstrate the kind of output that pre-trained SV2TTS model can generate, I'll let it explain itself using custom input text spoken by an existing voice from their training dataset.
Is cloning using an open source model. We're using a pre-trained speaker encoder and providing custom input text in the upper right white box. The pre-trained speaker encoder creates a vector representation of the speaker's voice. These embeddings can be seen in the lower left heat maps. The voice embeddings and text embeddings are combined by a synthesizer to produce the null spectrograms in the lower right-hand corner. Lastly, a vocoder takes these spectrograms and generates an audio waveform, which you are hearing right now.
So the pre-trained SV2TTS can be used to generate speech using arbitrary text from one of a few hundred or so voices, one on which we demonstrated in the last slide. It can also be fine-tuned to generate speech in an arbitrary voice using arbitrary text. All we need to do is collect some audio samples, which are freely available to record via the internet, load up a few of the resulting M4A files, and use the pre-trained SV2TTS model as a feature extractor to synthesize new speech waveforms. Listen to a snippet of one of those M4A samples of Tom Hanks that we used for fine-tuning now.
Or the 30 building, you're not taking electronics over in the 10 building.
So examples of Mr. Hanks like that one, and using them as new inputs, I'll demonstrate the result of fine-tuning on a few texts that were chosen by us to resemble commentary that is representative of some broader I/O themes.
It demonstrates that we have a common enemy, but I would not count on this relationship to go beyond that. This regime has shown it will not hesitate to burden good relations for its own financial gain. The leaked documents clearly show that the foreign minister is corrupt and that he has misdirected funds. The intelligence services have indicated that these anti-government protests have been organized by foreign entities. They are bent on stirring up trouble and causing harm to the people of our country.
You'll notice that the timbre of the voice is very similar to Mr. Hanks, and that it's able to synthesize Tom's voice from custom text. Neither the text nor the voices have been explicitly contained in any of the original training datasets. In principle, I could generate such cell phone quality speech audio from arbitrary targets, as long as I could acquire audio or video files of them on the internet, and then make that speaker dictate from arbitrary custom text that I control. It's also worth noting that I don't even need a GPU to do this. The pre-trained model was fine-tuned locally using my laptop's own CPU cores, which also suggests that quality improvements are possible as well. Our last proof of concept will be in the text domain, where we'll demonstrate how to fine-tune GPT-2 in order to generate custom social media posts reflecting narratives stemming from a social media I/O campaign. GPT-2 is an open-source neural network that was trained on the causal language modeling task. The objective here is to predict the next word in a sentence from previous context, meaning that a trained model ends up being capable of language generation. If the model can predict the next word accurately, it can be used in turn to predict the following word, and then so on and so forth until eventually the model produces fully coherent sentences and paragraphs. In terms of architectures, which you can see here on the right side of the slide, transformers use attention to decrease the time required to train on enormous datasets, and they also tend to model lengthy text and scale better than previous generations of feed-forward and recurrent neural networks. Again, to emphasize the sheer amount of training data this thing was pre-trained on, GPT-2's training dataset consisted of over 40 gigabytes of internet text data extracted from over 8 million reputable web pages based on high Reddit karma. An example of GPT-2's output generation is pictured here for predictions primed by the phrase, "It's disgraceful that." The passage displays relatively formal grammar, punctuation, and structure that corresponds to the text present within their original dataset. I won't read through the entire passage now, but you can visit our blog post at the link below for more technical details, or download this slide deck for closer inspection. Overall, though, the content is prosaic, sets a scene up between a few different people, and includes dialogue of their interactions in a consistent and logical fashion. So to make GPT-2's output text appear more like social media posts with their shorter length, informal grammar, erratic punctuation, and syntactic quirks like hashtags and emojis, we fine-tuned it on a new language modeling task using additional training data. This data consisted of open-source social media posts from accounts operated by Russia's famed Internet Research Agency, or IRA, troll factory. For fine-tuning, we simply processed social media posts from these open-source datasets through the pre-trained model, whose activations were then fed through adjustable weights into a linear output layer. These fine-tuned text generations are formatted like something we might expect to encounter scrolling through social media. They're short, yet biting, express certainty and outrage regarding hot-button political issues, and contain emphases like an exclamation point. They also contain idiosyncrasies like hashtags and emojis that positionally manifest at the end of the generated text, depicting a semantic style regularly exhibited by actual users. So now that I've gone over some background and technical proof of concepts for how to leverage fine-tuning of open source neural networks for customizable purposes, I'll hand it over to Lee to show you how these capabilities can in turn be leveraged for I/O campaigns.
Hi everyone. Once again, my name is Lee Foster, and I run the Information Operations Analysis team at FireEye, which is dedicated to identifying and tracking state-backed cyber-driven influence campaigns online. Now that Phil has detailed the various technical aspects of synthetic media generation and demonstrated the ease with which existing models can be fine-tuned for specialist use cases, I'm going to explore the risks that such capabilities present in the information operations space. Now, the misuse of synthetic media for I/O has been hotly debated in various circles for a few years now. Some argue it will change the game to such an extent that it will become difficult to ascertain whether anything we consume online is true or false. Others argue that the threat is way overblown and that there are much simpler yet still effective influence and manipulation techniques that negate the need for threat actors to even entertain the use of synthetic generation. However, the majority of such debates are often overly narrow, over-prioritizing or focusing only on deepfake videos without sufficiently taking into account other types of synthetic media that are easier to produce from a technical standpoint and can be more readily integrated into the types of I/O campaigns my team identifies daily. So what kinds of techniques do we see I/O actors use currently? They are numerous, and while I don't have time to touch on more than a tiny proportion, it's useful to highlight a few current tactics that we've observed that would be particularly conducive to leveraging synthetic media. Last year, for example, my team uncovered an influence campaign we termed Distinguished Impersonator, which we assess is being conducted in support of Iranian political interests. One prominent campaign tactic involves fabricating journalist personas and reaching out to real-world experts and political figures to disingenuously solicit audio and video interviews that advance an Iranian political agenda. The link at the bottom of the slide here directs to some of our public reporting on this campaign if you're interested in more detail. Another common tactic we see is the development of cross-platform online personas that are used to infiltrate target groups or disseminate fabricated content to specific audiences. There are many examples of such activity out there, perhaps most famously the Russian Internet Research Agency that Phil mentioned earlier. However, another recent example is the Ghostwriter campaign that my team has uncovered, a campaign that has leveraged website compromises and used multiple well-developed personas to disseminate fabricated content, such as falsified correspondence of officials in Eastern Europe in support of Russian security interests. Another extremely common tactic is the use of large networks of inauthentic social media accounts pretending to be random, unaffiliated individuals, which are then used to amplify political narratives across platforms and geographies. One prominent recent example of this are the networks we have identified operating on Western social media platforms pushing pro-China narratives around issues such as democracy protests in Hong Kong and the COVID-19 pandemic. The link at the bottom of this slide directs to a presentation me and a colleague gave on some of this activity last year. And finally, other very common techniques include the use of appropriated photos of real individuals to backstop false personas, and the repeated use of identical text on social media to astroturf political commentary. Synthetic media has real potential to exacerbate the use and effectiveness of these tactics. For example, we already regularly observe the use of artificially generated profile photos for inauthentic social media accounts and false personas. But we can readily envision an escalation of this tactic, in which convincing personas are created using artificially generated profile photos trained on images of real people from a target group or geography that correspond to, say, a particular minority group and are used to instigate political conflict or incite animosity and violence. The use of synthetically generated audio interviews in a campaign similar to the pro-Iran Distinguished Impersonator campaign I mentioned previously, trained on a real political expert's voice, would lower an actor's burden by removing the need for them to engage in direct outreach to real people, which would also make attribution more difficult for investigators by reducing available leads such as contact details and modes of communication between the actor and target. and synthetic media would drastically lower the barriers to actors seeking to disseminate diverse text-based content at scale, reducing the investment required to manually create a large corpus of content and the need to repeatedly reuse snippets of identical text. The unifying theme behind all these example use cases is that they would materially help threat actors scale campaigns at low cost and better evade detection. Fine-tuning in particular presents a problem for blue teams, as it allows threat actors to evade classifiers and detection models that are built for pre-trained outputs. This is worrisome as a would-be threat actor, my fine-tuning datasets are private and unknown to the defender at test time. To illustrate this, we performed detection experiments in the text domain using GPT-2. After releasing GPT-2, OpenAI released source code and a pre-trained classifier called Roberta, which does not share the same architecture or tokenizer as GPT-2, that could reliably discriminate between GPT-2's own output generations and its original training data of high karma Reddit posts. We use Roberta first to verify their findings that one can reliably differentiate between fabricated GPT-2 generated text and the authentic GPT-2 training dataset, which is shown by the blue bars in the plots on the right. The first plot shows the scores returned by the detection model on text generated by the pre-trained GPT-2 model. The fact that the distribution is skewed all the way towards the right, close to 1, means the detection model, with a classification threshold of 0.5, can easily classify the generations as fake. This results in an accuracy score of over 97% for the detection model, as shown in the lower right plot. However, when we perform the same exercise using the pre-trained classifier to try to differentiate our fine-tuned I/O generations that Phil detailed earlier, the accuracy dipped to around 78%, as the distribution of scores output by the classifier for these fine-tuned generations shifts closer to chance, i.e. 0.5, as shown in the red in the top right plot. So if threat actors were to fine-tune on a custom dataset they themselves collated, this would present a problematic asymmetry between the data used to create the synthetic generations and the data with which blue teams would have access to or knowledge of with which to build a commensurate detection model. So as mentioned previously, we already frequently see I/O campaigns use synthetically generated profile photos for inauthentic accounts on social media. And here are some examples of recent intelligence reports on I/O activity my team has detected that I screenshotted to give you a sense of both the scale and diversity of this current use case. So we've seen the use of synthetic profile images in the pro-China networks that I mentioned previously, in a recent operation that appeared designed to support government officials in a region of Argentina, to backstop a fabricated journalist persona that was used to amplify awareness of a defacement of a news agency's Twitter account in Kuwait, and in a social media operation that promoted Cuban government political interests. And this is what that looks like in practice, along with some of the markers of inauthenticity that often clue us into the images being artificially generated. You can see in these examples from one of the pro-China networks the common format of a closely cropped headshot with a blurred background, anomalies around the ears and neck, and difficulties with fully rendering glasses. Phantom hair strings being generated outside a credible area. Common issues with the rendering of earrings and shoulders, as you can see in this image that was used in the Argentina-related activity set. And hilariously, in these last two examples, the operators behind the pro-Cuba network didn't even bother to crop out the text placed by the "this person does not exist" tool, stating that the images were generated with StyleGAN prior to use. Now, one of the criticisms that is regularly leveled at concerns about the misuse of synthetic media is the high level of effort required on the part of malicious actors. However, it is important to note that in many cases, the difficult technical work has already been done by organizations and individuals who have developed and released either ready-to-use applications and services or source code that performs generations for a number of non-malicious motivations, including hobbyism, i.e. personal learning or simply for the fun of it, an ethos of the open sharing of technical research, and direct commercial applications for marketing and advertising, corporate communications and training materials, and even for the creation of assets in video games and other consumable media. Synthetic media as a service is particularly worrisome, as it is important to note that we have already seen actors outsource the organization and conduct of specific influence campaigns to public relations firms and other organizations that possess a nuanced understanding of how to target audiences and create engaging content. For example, Facebook has announced multiple takedowns of accounts and pages on their platforms engaging in foreign interference that were operated by PR firms. Last month, they removed assets operated by a Canada-based firm that engaged in election-related influence activity in South America, and in May removed assets operated by a Tunisia-based firm that poses locals and independent news outlets in sub-Saharan Africa. It does not take much for IO actors to make a similar leap to the use of commercial providers of synthetic media generation to augment their campaigns and further bypass the technological barriers to entry, beyond the use of transfer learning that Phil detailed earlier. Indeed, the adoption of commercial outsourcing would provide numerous benefits to IO actors, including providing multiple avenues for operational deployment, which would reduce direct ties back to sponsors and make campaign attribution more difficult for investigators, increasing the diversity and specialization of both assets and content by drawing on external expertise, lowering the investment and expertise required by a sponsor themselves to partake in synthetic media augmented I/O, and adding multiple layers of anonymity and plausible deniability against accusations of responsibility for any particular campaign. So what should we take away from everything that Phil and I have discussed throughout this talk? First, and perhaps obviously, it highlights the need for the research community to focus attention on the development of technical detection and mitigation capabilities. There are already some organizations focused on this mission, and multiple avenues of research that can and should be pursued. These include statistical and machine learning approaches to detecting synthetic media, as well as the identification of fingerprints and forensic indicators, such as text-based grammatical and image-based positional indicators that can be detected both manually and in automated ways. Other avenues of effort could focus on the content authentication side of the challenge, developing ways of allowing producers to verify, mark, or sign legitimate content, for example through the insertion of trackable metadata at the content generation stage. And similarly, ways for the developers of synthetic generation tools to watermark those tools' output. And then, of course, there are hotly debated policy considerations around content moderation, social media account registration and authentication, and fact-checking that are currently nowhere close to being resolved. Technical approaches to the challenge alone won't suffice, however, and there's the human aspect to all of this, which we've tagged patching human perception. This includes the importance of building a community-wide approach to mitigating the human impacts of synthetic media augmented I/O and ensuring communities of researchers coalesce around approaches to overcoming the challenges of detection. Threat modeling how synthetic media may be used in future I/O campaigns, and encouraging commercial providers of synthetic generation tools to acknowledge the potential for their abuse by threat actors and verifying customer use cases prior to service provision. Indeed, the Sankey diagram here is the output of an exercise we did in which we surveyed the offerings of some current commercial providers of synthetic media generation services, which we defined as those that explicitly offer paid services instead of or in addition to free tools. Looking at image, video, and voice generation offerings, we asked two questions. What specific use cases do these providers market themselves towards, and do they explicitly acknowledge the potential for misuse of their services through any kind of ethics statement? Of the 14 companies we looked at, less than half had any kind of ethics statement. Perhaps equally, if not more concerning, some firms did not even feign to market themselves to any particular use case whatsoever, effectively leaving it up to end users to determine the purposes their synthetic generations might even be used for. Only a couple of companies, specifically in the voice generation space, explicitly stated that they verify and sign off on their customers' end use cases before agreeing to provide services. And there also remains the need for raising awareness and educating consumers of online content about the risks of synthetic media in a responsible manner that doesn't misrepresent the threat, as well as developing legal and regulatory approaches to dealing with information operations and synthetic media. The final takeaway we want to raise is that we are really in the calm before the storm stage of synthetic media's use in information operations. As Phil highlighted, these capabilities continue to become cheaper, both monetarily and in terms of computing power required, easier, more pervasive, and their outputs ever more credible. And there are numerous trends that risk further escalation of the threat. The amount of effort required to fine-tune existing models or train new models will continue to decrease. Multimodal content will likely one day incorporate synthetically generated text, images, and audio in single pieces of content. Image generation capabilities and even commercial services are already moving beyond merely headshots and facial generations to full body shots and advanced video generations. And end users will enjoy increasing control over and ease of content generation, both through being able to steer generations towards particular attributes at more granular levels, and by being able to leverage an increasing amount of low-code or no-code applications for content creation. And one really important factor to keep in mind is user susceptibility to misleading content. Some criticize the threat of synthetic media as being overblown because there are still telltale signs of inauthenticity in contemporary synthetic generations. But even if we set aside all the trends I just mentioned, it is critical for us to acknowledge that synthetic generations don't need to be overwhelmingly credible to have that desired effect. People are accustomed to consuming short, authoritative, error-riddled social media text at speed without dwelling too much on its linguistic features or origin. They are accustomed to consuming poor quality audio and video snippets, and most users are unlikely to give a Twitter account's profile image more than a cursory glance as they scroll through their feed and ingest the written content at rapid speed. All of this points to a crucial consideration. The quality bar does not need to be particularly high when it comes to synthetic generations. It only needs to remain good enough for a majority of users to not question it in a world characterized by high-speed, high-volume information consumption. So to summarize, fine-tuning for generative impersonation in the text, image, and audio domains can be performed by non-experts, and it can be weaponized for offensive social media-driven information operations. Detection, attribution, and response is challenging in scenarios where actors can anonymously generate and distribute credible fake content using proprietary training datasets. And we as a community can and should help AI researchers, policymakers, and other stakeholders mitigate the harmful effects of open source models. We'd like to thank you for your time today and look forward to answering your questions.
All right, folks. So thanks for your interest and attention in this talk. I see a few questions in the chat. We have a few minutes here, so if you have some more, please get those in. First, want to address, sorry about the audio quality. So what I'll do is I'll drop a link to our blog post that should have the audio samples there for people to take a listen to. So I'll do that now. And also, so someone had asked about the availability of a paper. This blog post would be the closest thing to that from our side. If the question was more pertaining to the papers we discussed in the talk, our slides will be available on the Black Hat website, I think soon. And we made sure to put references at the bottom of each of those slides. Otherwise, you can just Google these. One of the beauties of this I guess the thesis here is that these are all open source, all these models we used. So not necessarily trying to make this a how-to guide for bad actors, but you yourself can go up and try and play around with these things. But otherwise, let me hand it off to Lee for another one of these questions.
Thanks, Phil. I know we've only got like a minute and a half here, so I'll quickly breeze through the questions that came up for us here. So Robert asked about companies like Lyrebird have made much of their willingness to restrict the sale of model output. What are your thoughts on these kinds of models from the perspective of future concerns? As I alluded to in one of the slides there, we did note that a couple of firms in the voice space actually do vet use cases and confirm that the consumer has the legal right to use the voice that they're trying to fabricate. And so I do think that this is a good model. In general, the question is, how do you try to normalize this across this entire industry when you have kind of very different tiers of players here? Patrick asks, for the PR and marketing firms engaged in this, have you found a common pricing model? If your question is about the outsourcing of I/O campaigns in general to PR firms, no. And I would presume that those are kind of custom spec'd. But on the synthetic generation, a couple of models did emerge. One is kind of a timed use model and access to a services API. Another is kind of a custom quote depending on the scale of the project. And then finally, Gabriella asks, have you seen any liability cases for using AI images that actually look like a real person? If you're talking from a legal perspective, no, not that I'm aware of. But definitely, something to kind of look into, I think, for sure. I think we're out of time now. So if there are other questions, please hit us up on email or Twitter, and we'll be happy to chat with you.